IP multicast is an efficient networking method that sends a single stream of data from one source to multiple interested receivers simultaneously, using special group addresses, like Class D in IPv4, 224.0.0.0-239.255.255.255, instead of sending individual copies, unicast, or flooding everyone, broadcast, saving bandwidth for applications like video conferencing, IPTV, and stock tickers. Network devices, routers, intelligently forward packets only to segments where members of the group exist, using protocols like IGMP, between hosts/routers, and PIM, protocol-independent multicast, for routing. Unicast, broadcast, and multicast are three primary methods used to transmit data across a network, distinguished by the number of intended recipients. 1. Unicast, one-to-one. Unicast is the most common form of communication. It sends data from a single sender to a single specific destination. How it works: the sender includes the unique IP address of the recipient in the data packet header. Characteristics: it provides the highest degree of personalization and can use secure, session-based protocols like TCP. Examples: browsing a website, sending an email, or downloading a file. 2. Broadcast, one-to-all. Broadcast sends data from one source to every device on a local network segment simultaneously. How it works: a special broadcast address, example 255.255.255.255 for IPv4, is used to tell every device in the subnet to process the packet. Characteristics: it is often inefficient because it forces every device to process the data, even if they do not need it, which can cause network congestion. Examples: ARP, Address Resolution Protocol, requests and DHCP address requests. 3. Multicast, one-to-many. Multicast allows a sender to transmit data once, which is then delivered to a specific group of interested recipients. How it works: recipients subscribe or join a multicast group using the Internet Group Management Protocol, IGMP. The network replicates the data stream only where paths diverge to reach different members. Characteristics: it is highly efficient for bandwidth-intensive data because it avoids sending separate copies for every receiver, unlike unicast, while avoiding flooding uninterested devices, unlike broadcast. Examples: IPTV, live TV streaming, online multiplayer gaming, and video conferencing. Comparison summary feature: unicast multicast broadcast model: one-to-one, one-to-many, one-to-all recipient, S. A single device, a specific group. All devices on segment. Bandwidth use high for many recipients. Low/efficient. High/can congest. Addressing unique IP address. Class D range, 224.0.0.0/4, subnet broadcast address. How it works: 1. Group formation: a sender transmits data to a special multicast group IP address, example 239.1.1.1. 2. Membership: hosts interested in the data join the group using protocols like IGMP, Internet Group Management Protocol. 3. Efficient routing: routers use multicast routing protocols, like PIM, to build distribution trees, ensuring packets travel only along paths to group members, not to everyone. 4. Data delivery: a single copy of the packet travels from the source, routers replicate it only where needed to reach different branches of the group, delivering it to all subscribed receivers. Key benefits: bandwidth savings, dramatically reduces network load and server processing by avoiding multiple streams for the same content. Scalability, handles large audiences efficiently, ideal for mass distribution. Real-time efficiency, perfect for time-sensitive applications like live video. Common applications: video conferencing and IPTV, Internet Protocol television, financial data feeds, stock quotes, news, distance learning and corporate communications, online gaming and e-commerce. Multicast address ranges: IP multicast uses reserved address spaces managed by IANA, IPv4, Class D 224.0.0.0 to 239.255.255.255. Local network control, 224.0.0.0/24, example OSPF, RIPv2. Source-specific multicast, SSM 232.0.0.0/8. Administratively scoped, 239.0.0.0/8 for private use within an organization. IPv6, always begins with the prefix FF00:8. Key components and protocols: component/purpose protocol multicast, the device originating the data. Source multicast, a dynamic set of receivers interested in the same stream. Group IGMP/MLD, used by hosts to join or leave groups on a local network. PIM, the primary protocol used between routers to manage distribution trees. IGMP, a layer 2 feature that allows switches to forward multicast traffic only to ports with snooping active receivers. In this following scenario, we have a sender in subnet A, example 10.1.1.0/24, and receivers in subnet B, example 10.2.2.0/24, communicating via group address 224.1.1.1. Step 1. Receivers express interest, IGMP and IGMP snooping. Before data is sent, the receivers in subnet B must signal that they want the traffic. 1 host join. A host in subnet B sends an IGMP membership report for group 224.1.1.1. 2 switch action. IGMP snooping. The layer 2 switch in subnet B snoops this IGMP message. Instead of flooding the traffic to everyone later, it notes which specific port the receiver is on. 3 router registration. The local router for subnet B, the last hop router, receives the IGMP report and adds an entry to its multicast routing table, asterisk, 224.1.1.1, meaning send any traffic for this group to subnet B. Step 2. Building the path, PIM sparse mode. Because the sender is in a different subnet, the routers must build a tree to connect the two networks. 1 PIM join. The router in subnet B sends a PIM join message toward the rendezvous point, RP, a central meeting point router in the network. 2 tree formation. Every router between subnet B and the RP creates a forwarding state for 224.1.1.1, forming the shared tree. Step 3. Sending the data, multicast forwarding. 1. Source transmission. The sender in subnet A starts sending data packets with destination IP 224.1.1.1. 2 registration. The router in subnet A, first hop router, sees this traffic. It encapsulates the data and unicasts it to the RP to let the network know a source is active. 3 RP forwarding. The RP receives the data, decapsulates it, and sends it down the shared tree towards subnet B4. Shortest path switchover. Once the subnet B router starts receiving data, it may optimize the path by joining a source tree directly towards subnet A, bypassing the RP for lower latency. Step 4. Local delivery, MAC addressing. 1. L3 to L2 mapping. When the subnet B router forwards the packet onto the local LAN, the destination IP 224.1.1.1 is mapped to a specific multicast MAC address, 01:00:5E01:01:01:01. 2 switch forwarding. The switch sees the multicast MAC address and, thanks to the IGMP snooping performed in step 1, it only sends the packet out of the specific ports where receivers are connected. Equipment summary. Sender/receiver, use IGMP to signal group membership. Switches, use IGMP snooping to prevent flooding all ports within a VLAN. Routers, use PIM to route traffic between subnets and RPF, reverse path forwarding, to ensure no loops occur. IP multicast group address and its MAC address. IP multicast group addresses are mapped to MAC addresses using a specific algorithmic translation rather than the dynamic resolution, ARP, used for unicast traffic. This process differs significantly between IPv4 and IPv6. IPv4 multicast mapping. IPv4 multicast addresses, Class D, 224.0.0.0 to 239.255.255.255, are mapped to a reserved IANA MAC address range starting with the prefix 01:00:5E. 1 reserved prefix. The first 25 bits of the MAC address are fixed as 01:00:5E0 in binary, 01-00-5E00 to 01-00-5E7F in hex. 2-bit mapping. The last 23 bits of the IPv4 multicast address are directly copied into the last 23 bits of the MAC address. 3 ambiguity. 32:1 ratio. Because an IPv4 multicast group has 28 variable bits but only 23 are mapped, 32 different IP addresses map to the same MAC address. For example, 224.1.1.1 and 239.1.1.1 both map to 01:00:5E01:01:01:01. Example calculation, 224.1.1.1 IP, binary 111000000000000000001.000000001, bold equals last 23 bits, MAC prefix, 01:00:5E0. Binary 000000001:0000000000001:0101110:0, combined, 01:00:5E01:01:01:01 IPv6 multicast mapping. IPv6 multicast mapping is more straightforward because it uses more bits, reducing overlap. 1 reserved prefix. IPv6 multicast MAC addresses always begin with 3333. 2-bit mapping. The last 32 bits, 4 bytes, of the IPv6 multicast address are copied directly to the last 32 bits of the MAC address. Example calculation, FF021 IP, last 32 bits 00:00:00:01 MAC prefix, 3333 resulting MAC, 3333:00:00:00:01. Comparison table feature IPv4 multicast IPv6 multicast MAC prefix 01:00:5E, with 25th bit as 0, 3333 mapped bits last 23 bits of IP last 32 bits of IP overlap ratio 32 IP addresses, 1 MAC variable, much lower, reserved 01:00:5E00:00:00:00, 3333:00:00:00:00, range 01:00:5E7FFFFF 3333FFFFFFF. Multicast routing. Multicast routing is the process by which network routers build and maintain distribution trees to deliver a single data stream to multiple specific recipients while preventing network loops. Unlike unicast routing, which focuses on the path to a destination, multicast routing focuses on the path back to the source. One core mechanism, reverse path forwarding, RPF. The most critical check in multicast routing is reverse path forwarding, RPF. How it works: when a router receives a multicast packet, it looks up the sender's IP address in its unicast routing table. The check: if the packet arrived on the same interface the router would use to reach that sender, the check passes, and the packet is forwarded. Purpose: this prevents routing loops. If a packet arrives on an incorrect interface, it is dropped because it is likely a duplicate or part of a loop. Two multicast distribution trees. Routers organize these paths into trees to ensure efficient data delivery. Source-based trees, shortest path tree /SPT route, the actual source of the traffic. Notation, written as S, G, source and group. Advantage, uses the most direct path between source and receiver, reducing latency. Shared trees, RP tree /RPT route, a central meeting point called a rendezvous point, RP. Notation, written as *G, any source for that group. Advantage, more scalable because routers only need to remember one path to the RP rather than a path for every individual sender in the network. 3. Primary protocol, PIM, Protocol Independent Multicast. PIM is the dominant protocol used between routers to build these trees. It is independent because it relies on existing unicast routing tables, like OSPF or BGP, rather than its own discovery protocol. PIM sparse mode, PIM SM. The pull model. Traffic is only sent when a router explicitly requests it via a join message. It typically starts with a shared tree to the RP and then may switch to a source tree for better performance once data starts flowing. PIM dense mode, PIM DM. The push model. It floods traffic to every corner of the network first, then prunes branches that have no interested receivers. This is generally considered legacy and is less efficient for large networks. PIM source-specific multicast, SSM. A more modern version where receivers explicitly specify the source they want to receive from, building an SPT immediately without needing an RP. For coordination with local networks. For routing to work across subnets, the routers must know where the receivers are. IGMP/MLD, hosts use these protocols to tell their local router they want to join a group. MSDP, Multicast Source Discovery Protocol, used to share information about active multicast sources between different PIM domains or organizations.